expression. In question 1, we've got f of x here defined to be 9 minus x squared for x being greater than or equal to 0, and we need to write down the range of f. So I will start by stating that x squared is greater than or equal to 0 for all real values of x, including those values of x that are greater than or equal to 0. Now if I multiply both sides by -1, I get minus x squared being less than or equal to 0. And if I add 9 to both sides, I get 9 minus x squared being less than or equal to 9. So what I'm doing here, I'm reconstructing the expression for f of x. So this leads to f of x being less than or equal to 9, which is exactly the range of f. It's the output that can come out of f of x. So if I input x being greater than or equal to 0, the output will always be less than or equal to 9. Part B, we need to find the value of f of g of 1.5. So we're looking at a composite function. We know that we first apply the inside and then the outside. So we'll first do the g of 1.5 and then proceed with f. This means we're looking at f of 3 over the 2 times 1.5 plus 1. So I'm replacing x with 1.5 into the expression for g. This leads to f of 3 over 4. So I will be substituting 3 over 4 into the expression for f of x. So this is 9 minus 3 over 4 squared, which gives an answer of 135 over 16. In part C, we need to find g inverse, and I will start by writing y to be the expression for g of x, so 3 over the 2x plus 1. When finding the inverse of a function, the first thing to do is interchange the x with the y. So this leads to x is equal to 3 over 2y plus 1. And then we try to make y the subject of the formula. So I will cross multiply to get x brackets 2y plus 1 is equal to 3. I will expand to get 2xy plus x is equal to 3. So 2xy is 3 minus x, leading to y being 3 minus x over 2x. This means that g inverse of x is equal to 3 minus x over 2x. This is not the end of the story. We still need to provide the domain for the function g inverse of x. So to do that, I will start by considering g of x. I will sketch it, identify the range of g of x, and we know that the range of g of x will be the domain of g inverse, and this will provide me with the domain to complete my answer. So if I consider y is 3 over 2x plus 1, the first thing to do is consider asymptotes. So we know that when the denominator is 1, we've got a math error, we've got division by 0. So at 2x plus 1 is equal to 0, we've got an asymptote. So 2x is -1, which means that x is minus a half is the vertical asymptote. For the horizontal asymptote, I consider the behavior of y as x tends to infinity. So as x grows larger and larger and larger, the denominator goes to infinity, and 3 over infinity is 0. So as x goes to infinity, y goes to 0, and therefore y is equal to 0 is the horizontal asymptote. Furthermore, we can find the cut on the y-axis by setting x is 0. So when x is 0, we can see from the expression for y that y will be equal to 3 over 2 times 0 plus 1, which gives an answer of 3. That's the cut on the y-axis. This means I can proceed into sketching the graph of g of x. So we've got the axis here, we've got the asymptote that x is minus a half, and it's a reciprocal curve cutting the y-axis at 3. So this is what it looks like. We still have the restriction, however, that x must be greater than or equal to 0. So if x is greater than or equal to 0, then we're looking at this part only, what I have highlighted here in red, and we can see based on this that the range of g of x will be between 0 and 3, so 0 less than y less than or equal to 3. We can see that the 3 is attainable because x is greater than or equal to 0 is the domain of g of x. So we conclude that g inverse of x is 3 minus x over 2x, with the domain being x belonging to the reals and 0 less than x less than or equal to 3. Once again, I'm using the fact that the range of g of x is the domain of g inverse. So the 0 less than y less than or equal to 3 is the range of g of x. So the 0 less than x less than or equal to 3 is the domain of g inverse. In question 2a, we need to express cos x plus 2 sin x in the form r cos x minus alpha, where r is a positive constant and alpha is in radians between 0 and pi over 2. we need to be giving the exact value of r and the value of alpha in radians to 3 decimal places. So we've got cos x plus 2 sine x is r cos x minus alpha. So the first thing to do is expand the right hand side using the compound formula for cos a minus b. So this is r cos of x cos of alpha plus r sine of x sine of alpha. I will then be equating the cos x term, so cos x must be equal to r cos x cos alpha, and similarly 2 sine x should be equal to r sine x sine alpha. So this means we've got 1 is equal to r cos alpha and 2 is equal to r sine alpha, which takes me to 1 over r is equal to cos of alpha and 2 over r is equal to sine alpha. What I could then do is simply draw a right angle triangle. The angle alpha is at the base. We've got the cosine of alpha to be 1 over r, so it's adjacent over hypotenuse, and the sine is opposite over hypotenuse. So this means we can easily see that we can find r through Pythagoras theorem. So r is equal to 1 squared plus 2 squared and all square root, which gives an answer of root 5, whereas tan of alpha is equal to 2 over 1, which leads to alpha being shift tan of 2 over 1, which gives an answer of 1.107. And therefore we conclude that cos x plus 2 sine x is root 5 cos of x minus 1.107. In part B, we need to use the answer to part A to determine the exact maximum value of g of x, where g of x is defined to be 3 minus 7 f of 2x. So the first thing to do is write the expression for g of x in terms of x. So g of x is 3 minus 7, and we've got f of 2x being root 5 cos of 2x minus 1.107 according to the answer we obtained in part A. Well, we know that the cosine of any angle varies between plus minus 1, and therefore 7 root 5 cosine of 2x minus 1.107 will vary between plus minus 7 root 5. We can then easily see that the maximum for g of x will simply be 3 plus 7 root 5, and this will be attained when cos of 2x minus 1.107 is equal to negative 1, because if this is negative 1 together with the negative here, they will make plus 1, and therefore we've got the 3 plus 7 root 5. So in part II, where we need to find the smallest positive value of x, where this maximum value occurs, we simply need to solve cos brackets of 2x minus 1.107 is equal to negative 1. So 2x minus 1.107 is shift cos of negative 1. So we get 2x minus 1.107 is equal to pi, and therefore 2x is pi plus 1.107. I will divide everything by 2, so we've got pi plus 1.107 over 2, and this gives an answer of x which is equal to 2.12. In question 3, we've got the graph here of log y against x. We've got the straight line passing through the two given points, and we need to determine an equation for L. Well, using the fact that the gradient m is given by y2 minus y1 over x2 minus x1, we can simply see here that m will be 1.5 minus 0 over the 0 minus the negative 4.8. This gives an answer for the gradient of 5 over 16. We can also observe from the graph that the y-intercept c is 1.5, the cut on the y-axis, and therefore we conclude that log of y base 10 is equal to 1.5 plus the 5 over 16x. In part B, it says hence or otherwise express y in the form kb to the x, where k and b are given to three significant figures. Well, starting with the exact expression we were given for y is kb to the x. I will take log base 10 of both sides, so log y is equal to log kb to the x base 10, which means that log of y base 10 is equal to log of k base 10 plus log of b to the x base 10. I'm using the fact that the logarithm of the product here can be written as the sum of the logarithms, which can be further written as log of y base 10 is equal to log of k base 10 plus x log b base 10, where the power within the logarithm can come down here. So we've got x log b, which means I can simply compare with the expression we obtained in part A, and we can see that the log k base 10 is the 1.5, whereas the log b base 10 is the coefficient of x, so it's the 5 over 60. So I will be equating log of k base 10 being equal to 1.5, and therefore k is 10 to the 1.5, which gives an answer of 31.6. And also we've got log of b base 10 is equal to 5 over 16, and therefore b is 10 to the 5 over 16, which gives an answer of 2.05, and therefore we conclude that y is 31.6 times 2.05 to the power of x. In question 4, we've got f of x defined here, and we need to find the values of the constants a, b, c, and d, such that f of x can be written in the form of ax squared plus bx plus c plus d over x plus 3 squared. Obviously, I need to do long division here. If I expand the denominator, I can see that this will give me x squared plus 6x plus 9. And therefore, we need to do long division here with 2x to the power of 4 plus 15x cubed plus 35x squared plus 21x minus 4 with x squared plus 6x plus 9. Remember, we're trying always to match the highest order term found on the left-hand side. So x squared will be multiplied by 2x squared to get 2x to the power of 4. I also have 12x cubed, and then 9 times 2x squared is 18x squared, and I deduct. This will give me the 2x to the power of 4 cancelling out, and I also have 3x to the power of 3 plus 17x squared plus the 21x minus the 4. Now I will be multiplying x squared by 3x to get 3x cubed, so let me put a plus 3x here. So I've got 3x cubed plus 18x squared plus 27x, and I will subtract once more. This leads to negative x squared minus 6x minus 4. So I need a minus 1 here to give me minus x squared minus 6x minus 9. I put the negative sign. I can see that the negative x squared term will cancel out. The negative 6x will also cancel out. And the negative 4 minus the negative 9 will give me overall a 5. This means we can write f of x as 2x squared plus 3x minus 1 plus 5 over the x plus 3 squared. And therefore we conclude that the constant a is 2, b is 3, c is negative 1, and d is 5. In b, we have to find the integral of f of x using the answer we obtained here in part A. So this simply means we need to integrate 2x squared plus 3x minus 1 plus 5 brackets x plus 3 to the negative 2 with respect to x. Remember, we're increasing the power by 1, dividing by the new power. So we've got 2x to the power of 3 over 3 plus 3x to the power of 2 over 2 minus x plus 5 times x plus 3. And I increase the power by 1. I divide by the new power, and I also divide by the derivative of the bracket, which is 1. And we've got a constant of integration plus c. This leads to 2x cubed over 3 plus 3x squared over 2 minus the x minus 5 over x plus 3 plus c. Notice that the question was not asking you to simplify your final answers, so you could have scored full marks here. However, as a rule of good practice, it's good to simplify your answers, so this is the simplified answer to part B. In 5a, we need to prove the identity that cot squared minus tan squared is equivalent to 4 cot of 2x cosec of 2x. So I will start from the left-hand side. We're looking at cot squared x minus tan squared x. Well, I recognize this as a difference of 2 squares, so it's the cot of x minus tan of x times the cot of x plus the tan of x. Well, the next thing to do is express cot x as cos x over sin x. So we're looking at cos x over sin x minus the tan x, which is sin x over cos x. And then the second bracket is obviously going to be cos of x over sin of x plus the sin of x over cos x. And then the next thing to do is express everything over the same denominator. So for the first bracket, we've got a common denominator of sine x cos x, and in the numerator we're looking at cos squared x minus sine squared x. And for the second bracket, we also have a common denominator of sine x cos x, and in the numerator we're looking at cos squared x plus sine squared x. Well, I recognize the cos squared x minus sine squared x as the double angle for cos 2x, and then cos squared plus sine squared is 1. So we are looking at cos of 2x over sine x cos x for the first bracket times the 1 over the sine x cos of x. And I will then multiply top and bottom by 2 to see the double angle for sine 2x in the denominator, and similarly for the second term here. So what we're looking at is simply 2 cos of 2x over sine 2x for the first term times 2 over sine of 2x. Well, 2 times 2 is 4. Now cos of 2x over sine of 2x is cot of 2x, and then the 1 over sine 2x is simply cosec 2x, which is the right hand side as required. In part B, we are asked to solve for theta between minus pi over 2 and pi over 2, so we are in radians. 4 cot 2 theta cosec 2 theta is equal to 2 tan squared theta, giving our answer to 2 decimal places. Well, I will start by writing the left hand side as simply cot squared theta minus tan squared theta, which is equal to 2 tan squared theta. This means that cot squared theta is equal to 3 tan squared theta, and I will write cot squared theta as 1 over tan squared theta, and this is equal to 3 tan squared theta. If I cross multiply, I get 1 is 3 tan to the power of 4 theta, and therefore 1 over 3 is equal to tan to the power of 4 theta, which simply means that tan theta is either the fourth root of 1 over 3 or it's equal to the negative fourth root of 1 over 3. So essentially we're dealing with two simple trigonometric equations in tan theta. I will find my PV as the shifted tan of the fourth root of 1 over 3. Well, this gives an answer of 0.64976 dot dot dot, whereas the second PV will be shifted tan of the negative fourth root of 1 over 3, which gives an answer of negative 0.64976 dot dot dot. We're using the generating formula here to find all solutions. So for tan theta, this is simply the PV of 0.64976 dot 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 plus pi k. Remember, k is any integer, positive, negative, or 0. Or theta is the negative 0.64976 dot 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 plus pi k. If I set k to be 0, we get the values of theta being negative 0.65 or 0.65, and these are the only solutions within the range of negative pi over 2 up to pi over 2. In question 6, we've got the graph of the modulus of 3x minus 5a minus 2a. A is a positive constant. We are cutting the y-axis at point P and the x-axis at points Q and R, and we need to find, in terms of A, the coordinates of P, Q, R, and S, where S is the minimum point, the vertex of this graph. Well, the first thing to do is identify the equations of the line segments that give me the overall graph. So on the right hand side, I've got y is equal to 3x minus 5a minus 2a. So essentially the modulus here is behaving like a normal set of round brackets. So this simplifies to y is equal to 3x minus 7a. Whereas on the left hand side, we've got y is equal to minus brackets 3x minus 5a close brackets minus 2a. So y is equal to minus 3x plus 5a minus 2a, which means that y is minus 3x plus 3a. So obviously I'm dealing with two straight lines. I can easily identify that point P is the cut on the y-axis, it's the y-intercept of this straight line, so it must be having coordinates 0, 3a. So that's the answer to I. The point P has coordinates 0, 3a. Whereas for the point Q, it's the cut on the x-axis for this line here. I will be setting y to be 0, which means we've got minus 3x plus 3a is equal to 0. So we've got 3a is equal to 3x, which leads to a being x, and therefore we conclude that point P has coordinates a, 0. Now for the point R, this is the cut on the x-axis for the line y is 3x minus 7a. So for R, I will simply say that y is 0 again, which simply means that 3x minus 7a is equal to 0, leading to 3x is 7a, so x is 7a over 3, which means that point R has coordinates 7a over 3, 0. Now for the point S, remember S is the vertex of the graph here. So if we look at the original expression here, the vertex is found when the expression within the modulus is 0. And when the expression is 0, we simply see that y is negative 2a. So we can simply start by stating that at point S, we've got the expression within the modulus, so the 3x minus 5a being equal to 0, which leads to 3x is equal to 5a, and therefore x is 5a over 3. And if the expression within the modulus sign we said is equal to 0, this goes away, and we've got y is negative 2a, so the y coordinate is minus 2a, and therefore we conclude that the point S has coordinates 5a over 3, the negative 2a. Alternatively, you could have equated the two straight lines here, because that's the point of intersection between y is 3x minus 7a and y is minus 3x plus 3a. Find the value of x and then substitute to find the corresponding value of y. This should give you the same answer. In part B, we're asked to find in its simplest form in terms of a the values of x satisfying the given equation here. Now we can recognize the left hand side as being the graph provided, so I will start by considering y is the modulus of x minus 2a. So this is x minus 2a when the input x minus 2a is greater than or equal to 0. So again, the modulus part behaves like a normal set of round brackets. Or we can say it's equal to minus brackets x minus 2a when x minus 2a is negative. This simplifies to x minus 2a when x is greater than or equal to 2a, or minus x plus 2a when x is less than 2a. We can identify the vertex here as being at x is 2a, and when x is 2a, if we substitute it here, we can see that y is 0. So the vertex is found at 2a, 0, which means I can go back to my graph and add the extra sketch of the modulus of x minus 2a to see exactly how I can proceed to find the points of intersection and therefore the solutions to the given equation. So this is the graph we were given originally. I will first add the coordinates for P, Q, and R that we found in part A, and then I will add the graph of the modulus of x minus 2a. It consists of two straight line parts. The vertex is at 2a, 0, which lies between Q and R. So we can see that the solutions to the given equation are the points of intersection. We've got two of these, and therefore I will be equating the minus x plus 2a with the minus 3x plus 3a and the x minus 2a with the 3x minus 7a to find the two values of x. So on the left hand side we had minus x plus 2a is equal to minus 3x plus 3a, which leads to 2x is equal to a, and therefore x is equal to a over 2. Whereas on the right hand side we had x minus 2a is equal to 3x minus 7a, leading to 5a is equal to 2x, and therefore 5a over 2 is equal to x, a total of 2 solutions. In question 7, we've got the curve C defined to be x is 3 tan of y minus pi over 6, and we need to obtain an expression for the derivative with respect to x in the given form, with a and b being integers to be found. So starting with the expression for x, we can see that dx dy will be 3 times the derivative of tan y minus pi over 6. Well, the derivative of tan is sec squared, so I've got sec squared y minus pi over 6, and I should be multiplying by the derivative of the inside, and the derivative of y minus pi over 6 is 1. So we've got dx dy is 3 sec squared of y minus pi over 6, and I will be using the identity connecting sec squared with tan squared. We know that sec squared is 1 plus tan squared, so we're looking at 3 brackets 1 plus tan squared of y minus pi over 6. And then we know that tan of y minus pi over 6 is simply x over 3. So I will be substituting the tan square with x over 3 square. So we've got dx dy is equal to 3 brackets 1 plus x over 3 all squared and close brackets, which leads to dx dy being equal to 3 brackets 1 plus x squared over 9. I will express the bracket as a single fraction, so we've got dx dy is equal to 3 brackets 9 plus x squared over 9 close brackets, and we can see that the 3 with the 9 cancel out, leaving a 3 in the denominator, which simply means that to obtain an expression for dy dx, I will take the reciprocal of the right hand side, which is 3 over 9 plus x squared, and therefore we conclude that the constant a is 3 and the constant b is equal to 9. Now the point P with y coordinate pi over 3 lies on C. Given that the tangent to C at P crosses the x-axis at the point Q, we need to find in its simplest form the exact coordinate of Q. So it makes sense to use the fact that y is pi over 3 to find the corresponding x coordinate. So x will be 3 tan of pi over 3 minus pi over 6. So I'm substituting y is pi over 3 into the expression for x. This gives an answer of root 3. I will then obtain the value of dy dx when x is equal to root 3. This gives an answer of 3 over the root of 3 all squared plus 9. I'm substituting in the answer we obtained in part A, which gives an answer of 1 over 4. Now we know that a straight line with gradient m passing through the point x1, y1 has equation y minus y1 is mx minus x1. So we've got that y minus pi over 3 is equal to a quarter times x minus root 3. This is the equation of the tangent. And if we are crossing the y-axis, this simply means that y is 0. So I will substitute y is 0 to get minus pi over 3 is equal to a quarter brackets x minus root 3. I will cross multiply to get minus 4 pi over 3 is equal to x minus root 3, and therefore we conclude that root 3 minus 4 pi over 3 is the x coordinate of this point which we are trying to find, the point Q, which is the point at which the tangent crosses the x-axis. In question 8, we are asked to find in its simplest form the integral of 2 cos x minus sin x all squared with respect to x. So this is the integral we need to find. I will start by expanding the bracket to get 4 cos squared x minus 4 sin x cos x plus sin squared x dx. So we need to integrate this. So I will refer back to the expressions for the double angle formulae. We know that sine of 2x is equal to 2 sin x cos x. I will need this when I integrate the sin x cos x here. We also know that cos of 2x is equal to 2 cos squared x minus 1, which means that cos of 2x plus 1 is equal to 2 cos squared x, and therefore cos of 2x plus 1 over 2 is equal to cos squared x. So I will need this when I'm integrating the 4 cos squared x. And we also know that cos of 2x is 1 minus 2 sin squared x, which leads to 2 sin squared x is equal to 1 minus cos 2x, and therefore sin squared x is 1 minus cos of 2x over 2, and we will be needing this when we integrate the last term of sin squared x. So based on this, we can say that we're looking at the integral of 4 times cos of 2x plus 1 over 2 Then we've got minus 2 times the 2 sine x cos x. So I simply wrote the 4 as 2 times 2. And in the place of sine squared, I'll be writing 1 minus cos of 2x over 2 with respect to x. So this is the integral of 2 cos of 2x plus 2 minus 2 sine of 2x plus a half minus cos of 2x over 2. Remember that in integration we prefer multiple angles rather than multiple powers. I don't like the cos squared, I don't like the sine squared, but we are okay with the cos of 2x, the sine of 2x, and so on. So I will collect the like terms within the integral. So I've got 3 cos of 2x over 2 plus 5 over 2 minus the 2 sine 2x with respect to x, and I can proceed in integrating. Now the 3 cos of 2x over 2 will give me 3 over 2, and the integral of cos 2x will give me sine of 2x over 2. Remember, we need to divide by the derivative of the inside, and also the integral of cos is sine. Then for the 5 over 2, this is simply 5x over 2, and then minus 2, and the integral of sine is negative cos of 2x. And I also need to divide by 2 the derivative of the 2x and the plus c. Remember, we need to simplify our answer, so this leads to 3 sine of 2x over 4 plus 5x over 2. And then we also have plus cos of 2x plus c, which is the final answer. In question 9, we're given the curve C with the equation root of 3 plus 4e to the x squared, and we need to find dy dx, giving our answer in its simplest form. So the first thing I will do is write y as 3 plus 4e to the x squared and all raised to the power over half. So for dy dx, we will start by getting the power down the half. I deduct 1 from the power, so 3 plus 4e to the x squared to the power of minus a half times the derivative of the bracket. Well, the derivative of 3 is 0. The derivative of 4e to the x squared is 4 times the derivative of the inside, which is 2x. So 4 times 2x times e to the x squared. So we can see that we are left with 4x e to the x squared over the 3 plus 4e to the x squared square root. We then have that the point P with x-coordinate alpha lies on C, and given that the tangent to C at P passes through the origin, we need to show that x is alpha is a solution to the given equation. So the first thing to do is go back to the diagram here. We've got the point P with x-coordinate alpha and corresponding y-coordinate 3 plus 4e to the alpha squared and all square root. So these are the coordinates of P. I will find the gradient of OP because we know that this tangent here passes through the origin. So this will simply be the y-coordinate of P over the x-coordinate of P, rise over run, which means that 3 plus 4e to the alpha squared square root over alpha is the gradient of OP, which is also the value of dy dx at x is equal to alpha. So we will evaluate the expression we obtained in part A, substituting x is alpha. This is giving us 4 alpha e to the alpha squared over the 3 plus 4e to the alpha squared square root. And then if I equate this part with this part, the first obvious step is to cross multiply. So we get 3 plus 4e to the alpha squared with the square roots cancelling out because they are both the same expression within the square root, being equal to 4 alpha squared e to the alpha squared. And therefore I can collect everything on the right hand side to give me 0 is equal to 4 alpha squared e to the alpha squared minus 4e to the alpha squared minus 3. And we therefore conclude that x is alpha is a solution to the equation 4x squared e to the x squared minus 4e to the x squared minus 3 is 0 as required. In part C, we need to show that alpha lies between 1 and 2, so we are looking for a change of sign here. I will start by considering f of x to be exactly the equation we obtained in part B, and I need to evaluate f of 1 and f of 2, hoping for a change of sign, one of them turning positive, the other being negative. So I'll get my calculator, I press 1 and equal, so I store the 1 on my answer key, and I do 4 times n squared e to the n squared minus 4 e to the n squared minus the 3. So remember, the answer key is holding the value of 1. This is giving an answer of negative 3, which is less than 0. And then I want to find f of 2. So I simply do 2 equals, so I've stored 2 on my answer key now. I will press the cursor pointing upwards to obtain the previous expression. Now this time the calculator will evaluate the expression with the new value for the answer, the 2. So I press the equal sign. I get 652, which is greater than 0, which means we can safely conclude that since there's a change of sign and f of x is continuous, then alpha lies between 1 and 2 as required. Remember, you need to mention both the change of sign and the continuity of f of x for you to claim both marks here. In part B, we are asked to show that the equation in part B can be written in this form here. So this is the equation we had in part B. I will start by isolating the 4x squared e to the x squared term, which leads to 4x squared e to the x squared is equal to 4e to the x squared plus 3. I will divide everything by e to the x squared to get 4x squared is 4 plus 3e to the minus x squared. And then I will divide everything by 4 to get x squared is equal to 4 plus 3e to the minus x squared over 4. Now to make x the subject, I will take the positive square root. So x is 4 plus 3e to the minus x squared over the 4 and all square root. Now obviously the square root of 4 in the denominator is 2, and in the numerator I'm left with the square root of 4 plus 3e to the minus x squared as required. And finally in E, we need to use the iteration formula given here with the starting value of 1 to find x3, the third iteration, and also the actual value of alpha correct to 4 decimal places. So we are starting with x1 being equal to 1. I'm going to go on my calculator, I press 1 and equal, and then I will input the expression. We've got here the iterative formula. So we've got a half, so that's a half, and then we've got the square root of 4 plus 3, and we've got e to the minus the ans squared. So each time I'm pressing the equal sign, it's a new iteration. I press it once, I get that x2 is equal to 1.1296, and x3, I'm just gonna press the equal sign once more. I get 1.099719 which correct to 4 decimal places is 1.0997. And then to find the value of alpha, I will simply keep pressing the equal sign until the value on the calculator display stabilizes and I can safely conclude the value of alpha correct to 4 decimal places. So I keep pressing the equal sign, I'm stabilizing at 1.105, and after a few moments we see that the first few decimal places remain the same, so we can simply conclude that alpha is 1.1051 correct to 4 decimal places. In question 10, we've got the study of a population of fruit flies where capital F, the number of fruit flies, t days after the start of the study is given by this expression here. Now we need to use a given equation to find the number of fruit flies at the start of the study. Well, this simply means that we need to substitute t is 0 into the given equation, which leads to f being equal to 350 e to the power of 0 over 9 plus e to the power of 0, which gives an answer of 35 fruit flies. In part B, we've got that 200 fruit flies was the population 15 days after the start of the study, and we need to show that this leads to k being 1 over 15, ln of 12. So I will substitute capital F with 200, and this is equal to 350 e to the 15k. So I'm substituting t with 15 over 9 plus e to the 15k. I will cross multiply to get 200 times 9 plus e to the 15k is equal to 350 e to the 15k. I will expand the left hand side, leading to 1800 plus 200 e to the 15k is equal to 350 e to the 15k, and therefore we've got 1800 is equal to 150 e to the 15k. Now the 1800 with the 150 simplify, leaving a 12 on the left hand side. So if I take a ln of both sides, I get ln of 12 is equal to 15k, and therefore we have 1 over 15 ln of 12 to be the value of k as required. We are then told that when t is capital T, the number of fruit flies is increasing at a rate of 10 per day. That's the derivative here. And we need to find the possible values of capital T, giving our answers to one decimal place. So starting with the expression for f, notice I won't be substituting what we obtained for k in part B. I will keep it in terms of k, as it will make the whole expression easier to write down. And I will start by finding the derivative, so df dt. So this is the quotient rule of differentiation here. I differentiate the top to get 350k e to the kt, and I keep the bottom of 9 plus e to the kt, minus I keep the top of 350 e to the kt, and I differentiate the bottom, which gives me k e to the kt, and all of it over the bottom squared, so 9 plus e to the kt and all squared. Now notice that we've got a common factor of 350 k e to the kt, and we're left with 9 plus e to the kt minus e to the kt, close brackets, and all of it over the 9 plus e to the kt squared. So the e to the kt with the negative e to the kt in the numerator will simplify out, and this leads to an answer of 3150 k e to the kt over the 9 plus e to the kt squared. Now we have been told that the population is increasing at a rate of 10, so this means that df dt when t is equal to capital T is equal to 10, and if we substitute t with capital T in the expression we just obtained for the derivative df dt, we get 3150 k e to the k capital T over 9 plus e to the k capital T and all squared. That's the equation we need to solve. I will start by simplifying the 0 with the 0, and then I will cross multiply to get the 9 plus e to the kt and all squared is equal to 315 k e to the kt. I will expand the left hand side to get 81 plus 18 e to the kt plus e to the kt all squared is equal to 315 k e to the kt, and then I will let w be e to the kt, which leads to 81 plus 18w plus w squared is 315 kw. Collecting everything on the left hand side will lead to w squared plus 18w minus 315 kw plus 81 is equal to 0, and therefore we've got a quadratic in w, which says w squared plus 18 minus 315 k times w plus 81 is equal to 0. I can then use the quadratic formula to find the possible values for w. So we've got w is minus the b, the 18 minus 315k, plus minus the square root of 18 minus 315k squared, minus 4ac, and we've got the square root as well, and all of it divided by the 2a, so 2 times 1. So plugging this on the calculator, we get that w is equal to 31.621 ... or alternatively w is equal to 2.5615 ... Well, w is simply e to the kt, so e to the k capital T is 31.621 ... or e to the k capital T is 2.5615 ... I will take a ln of both sides, leading to kt is a ln of 31.621, or kt is a ln of 2.5615 ... So I can recover the values of t by simply dividing by k, so 1 over k ln of 31.621 ... or t is 1 over k ln of 2.5615 ... This gives answers for t of 20.8 or alternatively for t being 5.7.